Great. Thanks, Terry. Okay, welcome everyone. Thanks for coming. So what I'm going to talk about today is essentially shown in these two slides here. So we're going to do some image processing in the second part of the talk, but the first part I'll talk about this HR diagram tool, which is shown on the right side there, and show you how that works. So to start with, I have to move the floating thing, or actually I'll just hide it. So there's another URL for you to go to. If you want to pull this up, then you could have a look at it as I'm running through. So I'm going to actually start both of these parts just by running through some slides with some screenshots that I took talking about these things before we actually try them. So we're starting with Cluster Pro Plus, and if you go to the Skynet graph URL there in another tab, then there's a drop down, and you can just pull up the Cluster Pro Plus tool where you'll see various things that I'm going to show you. So Cluster Pro Plus is a tool that we built for creating HR diagrams of star clusters. One of the features that it has is the ability to just pull in catalog data. So in this case, this is M67. This is the whole field of M67, and I've plotted the Gaia data there. You can see the filters is just showing absolute magnitude in RP there, and BP minus RP in the Gaia filters. And so this is the whole field that M67 is in, and so we do have controls to be able to filter out cluster stars that aren't moving proper, that have different proper motion, so they're not moving with the cluster, and also filter out in distance so that we can isolate the cluster stars. And so that's what we see here. So this is right away, it's pretty quick, and you'll see how it's done when I show you. But so once we remove the field stars, then we're able to determine all kinds of things. So to start with, even just the number of cluster stars. So given the Gaia data set, we're able to the filters sort of tell us that there are about 1,100 stars in M67. Another really neat feature that you can see really well here is all the unresolved binaries in the cluster. So the in star clusters, if you have unresolved binary stars, then if they're equal mass stars, so they have the same color on the main sequence, they'll have double the brightness, which is 0.75 magnitudes brighter. And so all of the stars that lie above that isochrone model are actually binary stars in this cluster, and so we can pick those out and have a look at them. Or we can see the blue stragglers. So all of the stars over here, blue stragglers, or the red giant branch, horizontal branch, which is just this little clump here for this open cluster, and asymptotic giant branch, the stars that are there. And then there's also isochrone model fitting. So we've got the Girardi models built into this tool, and with sliders that we can adjust the age, the metallicity, and the reddening, and determine the cluster properties. So this is the model that I have plotted there for this cluster. So we can do things like in the classroom, pull this up, set various parameters, and look at what happens when you increase age. So going from a log of age equal to 7.5, increasing, you can see the main sequence star, or the stars fall onto the main sequence, or actually they fall below the parent main sequence of the cluster. And then we get a little bit of main sequence evolution. And also the turnoff point starts to move down. So we can, talk about that kind of stuff and explain how that works. So this is the model. We can also show what happens when you adjust the metallicity. So metallicity is extremely important for stellar evolution. And you can talk about that in a classroom and explain what happens when a star cluster has lower metallicity, and as we increase the value to the value for my best fit isochrone model there, or reddening. The reddening for this cluster is small. I think it's, I had set it to like 0.02, so I went with moving leftward over to 0. And you can see how 0 actually overshoots, and then 0.02 matches up a little bit better. Anyway, so we can adjust those parameters and talk about how that works, and pull up various examples for various clusters. So anyway, so those are the basic features. So there are highlights of this. So it's an interactive tool that you can give to students and have them use. You can interact and use it in the classroom, take questions, that kind of a thing. For investigating real cluster data, so either pulling in catalog data or to have students take their own data, their own images, and photometer them and plot. So we've got the Gaia proper motion and distance matching, and the ability to filter out and remove the field stars, and determine the number of cluster stars, identify all of the unresolved binaries in a cluster, which gives an opportunity to, as I said here, to teach about magnitudes and the magnitude scale. And so it's a tool that's kind of designed for use in a first-year classroom, so where you're just teaching people about colors and magnitudes and things, so we can understand all of these features of the HR diagram. Discuss other features of stellar evolution using real examples, and extinction and reddening. So as I adjusted the reddening, you see the isochrone model doesn't just make things redder as E of B minus V increases, but it also extinction also happens, and so so it also the isochrone also moves up. The turnoff point is something that we always teach students about in like a first year course. You learn about how as stars, the higher luminosity stars age more quickly or more rapidly and move off of the main sequence, evolve off the main sequence to become giants sooner. But when we look at like first year textbooks, you rarely see anything about metallicity, and metallicity is extremely important to how stars form and evolve, and so it's important. It's also just interesting conceptually, and it's actually a concept that that reinforces other stuff that we talk about when we're teaching stellar evolution. So the higher the metallicity of a star, there's just more screening inside the core, and so the temperature has to be higher and the luminosity increases, and so you've got effectively the star puffs up a little bit more, becomes a little bit more luminous and a little bit redder, which is exactly what happens when the star evolves off of the main sequence and becomes a red giant. So I don't know why we don't talk about metallicity very often in a first year course when it's a concept that teaching it actually helps to reinforce other things that we do normally talk about. So so this gives us a tool that enables us to talk about something we probably should be teaching. So let's try it out. So go to this tinyurl.com/Skynet-graph that I had posted before. So you might have that open, select the Cluster Pro Plus tool, and then rather than doing M67, which I showed, I just want everybody to have to try out M45. So we're going to do the Pleiades cluster, which is a large cluster, and we're going to pull up the Gaia data eventually. But to start with, we'll try APAS. So there's an object field, and so just type M45 in there and click the lookup button, and then there is our catalog lookup doesn't always give us the radius of a cluster for some reason. Like all of the clusters have a catalog radius, and for some reason some of them aren't working right. And so this one, for whatever reason, says 0.00. The Pleiades is a large cluster though, so so type in something like 3, and then before we pull up the Gaia data, I want you to check the APAS checkbox at the bottom and click fetch data. Has everybody gotten the error? So when you run fetch data on that one, yeah, I can go back. So M45 lookup, change radius from 0 to 3 degrees, check APAS, and then APAS is the AAVSO's all sky catalog. So we're just going to pull up what this is going to do is load all of the APAS data points within 3 degrees of the coordinates of the center of the Pleiades cluster. So when you click fetch data, you should get an error saying that that the Vizier lookup failed, and I set this up this way because I wanted to explain. What happens when we click fetch data is it doesn't just pull up the APAS catalog, it also simultaneously, it grabs the Gaia catalog for that field, and it matches up all of the stars in right ascension declination, their positions, in order to load the proper motion values and the distances for all of the stars. So because you set the radius to 3 degrees, we're pulling up all of the Gaia data points within 3 degrees of the Pleiades, and it's too many stars for the tool to handle. So we have to be a little bit smarter about it. So so we have a limit set to 50,000 Gaia stars, because otherwise you get more than 50,000 points on that tool. And so what we're going to do instead, the way to use this tool properly is setting the radius to something less, and a radius of 1 actually works. So set the radius to 1 and click fetch data again. Yeah, keep APAS selected, and we're just wanting to load APAS. You have to hit the lookup button. Yeah, so M45 and then click lookup. You need to have the coordinates and a radius. Yeah. So once you've, and you're welcome to just follow along. I think that those steps will actually get you through if you're waiting, just waiting to make sure that everyone has managed that step. So once you've got the data loaded, above the 2 HR diagrams, there's a proper motion graph showing the proper motion values for all of the stars in the field. And so take your mouse over to that proper motion graph and just zoom out In this case, the Pleiades is really close to us. It's at like 135 parsecs away, and it has a very large proper motion. If you look down at a proper motion in RA of 20 plus or minus 3, and proper motion in declination of minus 45.5 plus or minus 3, you'll see that there's a clump of stars in there. So all of the tool actually centered that graph on the Milky Way stars. That larger clump that you saw is everything in the Milky Way. Whereas if you go down to this, you've got the proper motion of the Pleiades. So if you set it to that and actually check the boxes that say plus or minus range and set that value to 3 milliarcseconds per year, and the proper motion in declination to plus or minus 3 milliarcseconds per year, and then go to the distance slider and change that to 0.135 kiloparsecs plus or minus 30, and check the plus or minus range on distance. So I'll just do everything that I have asked you to do real quick. So I look up M45, try a radius of 3 on APAS, fetch data. And there's too many stars, so then I change that value to 1. And I'll fetch the data again. There. So this is all of the stars in the field in APAS plotted absolute magnitude in V, which depends on the distance that I have set, which is wrong. So if I actually set that to 0.135, now the absolute magnitude values are correct. But over here, no, I don't want to do that. So what I had suggested to do is, these are all Milky Way stars. That's the proper motion of the Milky Way in that direction. But when you zoom all the way out, there's a clump of stars way down here. And that's the Pleiades stars with a proper motion in RA of 20 and minus 45.5 in dec. So set that to 20 plus or minus 3. Set this to minus 45.5 plus or minus 3, I said. And then we set the distance to 135 parsecs. Now that we have these constraints set, now we can actually increase our radius. So set it to something like 5. And then check the Gaia box to load the Gaia data set for this field. And now we're going to load all of the Gaia data points that are at this right ascension, that declination, out to a radius of 5 degrees, that are within these proper motion and distance constraints. So now when I fetch data, it pulls up all those stars. And you can see them there. It's a larger set. And you can see all of the different filters that we've got loaded. So APAS has BV, G prime, R prime, I prime. And then here are the 2 Gaia filters, and then the G, which is like an average of the 2. So if I go back here to my instructions, oh, I said 5. Apparently I said 4 there. We're fetching that, and then go back to here. I had a couple of notes here at this point. So first of all, our Gaia catalog that we have in this cluster tool is not the full Gaia catalog. We don't have all 2 billion data points loaded over the entire sky. What we have is the Gaia catalog for each of the known star clusters in the Milky Way star clusters catalog, centered there with out to a radius that's twice the cataloged radius of each cluster. So when I put the radius to 5 for the Pleiades, I'm not actually sure what the Milky Way star cluster's catalog radius of the Pleiades is, but it only would have gone out to whatever radius that we have loaded, which is double what the catalog radius for the cluster is. So it's a pretty good estimate. We can always make things bigger. We can add in more data points. So if you're interested in actually using this as a way of probing and testing and looking at, say, there are new cluster catalogs that people are producing from Gaia data using analyzing that, or with Rubin, you know, as we're gonna detect more clusters. If you want to use this tool with that, we would happily add more positions and radii, more Gaia points into our database. And so if you send me an email, d.j@usas.ca gets to me, then I can contact Vladimir back there and he can add more points in for us. So please do. All we need is the position and the radius that you're wanting. We just don't want to add all 2 billion points in. Also, just another point here. So this whole tool has been programmed in the last couple of years by an undergrad at UNC Chapel Hill, who last year he was in his first year computer science, and so he's just finished up his second year of computer science. We do have a bug with the 2MASS and the WISE lookup where it's not doing the proper motion and distance filtering for those two catalogs right now. He just wrote his last final this week, and that's one of the tasks that he's going to get to. So so that's why I didn't have you load in the 2MASS and WISE for this large radius. For most clusters, if you look at them, you know, you can pull them in, but you'll end up being limited in the way that you were with APAS to begin with. Anyway, so that's just the few notes. Okay, so now next thing, I'm not going to do this stuff because I want to get everyone's numbers here, but I just want to see if everyone's able to do it. Basically fit an isochrone model, fit the isochrone model to the data that you have pulled up there. So you've already got the proper motion and the distance values set. At the top left, for both the 1 and the 2 data sets where it's got BVV, change those to say BP, RP, RP, both of them, because we want to just show the Gaia data. The APAS data are lower quality data sets, and if you have a combination of APAS and Gaia loaded, then the number of stars that you see isn't the number from Gaia, it's the combination of the two. So one thing that we want to know is how many stars are there in the Pleiades star cluster. And so if you load only Gaia, it will show only the Gaia stars there in the number, and there should be 1,020 points out of 1314, I think is what I got when I changed that. So that's kind of interesting. We have an estimate here that there are 1,020 stars in the Pleiades cluster using this tool. That, of course, caveat, that counts 1 star for every unresolved binary. So we could actually do an analysis where we could do one better and actually add up all of the, there's a save data button down on the bottom sort of center, and you can export the data for this and look at the right ascensions and declinations of all of the unresolved binaries and you know, plot them in Excel or something like that. Pull them out and you could count 2 for all of those stars if you wanted a better estimate of the mass of the Pleiades. Anyway, once you've done that, the next step is to actually adjust your age, metallicity, and reddening values. Use the sliders to get a rough estimate. What I tend to do is I'll adjust the age to begin with, and just increase it somewhat, so that it's, you know, rough, a very, very rough estimate based on sort of eyeballing it. And then you want to adjust the metallicity to, when you adjust the metallicity, what you're going to do is pull the main sequence up to the cluster, up to the main sequence, because as metallicity increases, the core gets higher temperature and more luminosity, and everything kind of shifts up and to the right on the HR diagram. So you adjust, you've already got the distance set properly using Gaia. I guess I didn't talk about that, but you have a Gaia estimate of the distance, and you can adjust metallicity to get it close, adjust the age to get the turnoff roughly right, and then it should be offset. Sort of the isochrone model should be up to the upper left of, so that if you increase E of B minus V, you'll shift the isochrone model down into the right, and you should be able to get a pretty decent fit. Once you've used the sliders are sort of for course adjustment. If you take your cursor and you click on the number, you can use your arrow keys to advance by up or down by one value to whatever decimal place, and get those finer adjustments. Anyway, the reason why I don't want to do this is I'm kind of curious to see what everybody ends up getting, and once you get what you think is a decent isochrone fit, then go to this tinyurl.com/Messier45, enter your values in there, and then I'll get an average and plug those in, so that I don't have to stand up here and adjust things. Let you try. Terry, did you end up getting the Gaia catalog loaded?
I think it's fine, yeah.
Okay. Just checking out your questions. Good. Feel free to just speak up too, Terry, if you have questions, and everyone else too. Just say something if you have. See how everyone's doing. All right. /Messier45. I don't want to try and get signed into my Google account. I had forgotten about that. So I'm just going to pull up the spreadsheet. By the time I pull up this form, I imagine everyone will be have it sorted. Okay. There. Okay, we've got 6 responses, it looks like. Need to somehow quickly get onto someplace where I can post this. Here. Yeah, I've got a workaround for that, for the Google Sheet, rather than making a tiny URL. Matt, do you have, or actually, yeah, I sent it to Google Chat. Could you grab a link off of Google Chat and just put it in the Zoom chat? Or May? Just throw it in the Zoom chat so that I have the link. Oh. You're not on the Zoom. Yeah, right. Okay. Yeah, how do I? Are you able to access the Zoom, May? If I could figure out how to access the Zoom, that would work too. Just somehow need to get it to this computer, and it's a big long URL. I could also just type it in, but it's so long. Right, I can. You're right. Oh, but then I have to sign in, and it's not letting me sign into Google. Okay. Sorry. It's on the Zoom chat, but okay, there. Great. Okay, sorry, everyone. Got it. So here's our results. Hide that. So this is 7.77. Oh. Did that not? Apparently, I'm just not very good with spreadsheets. Oh my gosh. Why does it show a smart thing saying, do you want to go like this? And then you can't do it. Oh. It's somehow changed the text color. Like you're seeing. Okay, so this one says 8.25. And this one says what? What's the average metallicity? Okay. And then this one is that's fine. Yeah, we don't need. So the idea was to be able to take that and just enter those values in 8.25 minus 0.15 and 0.11 over here. So we wanted to go BP minus RP versus absolute magnitude there. So there's, I mean, even that's just super cool to me, the Gaia HR diagram of the Pleiades, that we can pull it up so easily. So we said minus 0.15, 0.11. Yeah, that's pretty good. I think that the metallicity actually is higher and maybe the reddening is less. I can't remember, but this actually down here is difficult to get at. And I'm not sure if that's because the metallicity actually is higher and well, not that high. But we've got some sort of thing going on there where it's more like that and we're getting at it, or that the isochrone models aren't handling that very well, because the isochrone model should be hitting like that almost looks like a turn on point kind of a thing, but the isochrone should include where the stars are at certain ages, so there shouldn't be a turn on onto the isochrone. Anyway, so is it an indication that that the models are imperfect? So we're actually kind of able to get at that level of analysis of whether or not we're happy with our models and model refinement and all of that. So it's kind of a tool that's great and accessible to first-year students, that's also kind of verges on research level. So anyway, so yeah, that's those were nice averages. Okay, so that's Cluster Pro Plus. So it can be used completely without taking any data if you want to. If you just want to use it in a classroom for teaching, pull up all kinds of star clusters and show your class real star clusters and their HR diagrams and talk about stellar evolution. There are lots of lessons that could be designed around just using it. The next thing that we're going to do is to actually show our color image processing tools that we've built in Skynet's fits analysis software package called Afterglow Access. So this is great and exciting, and I myself look at it and I understand the data and I know about graphing and all of that. But one of the things that's lacking if you're in a first-year class is a lot of first-year students aren't great at interpreting graphs and seeing how things work. So actually having an image, a color image to be able to look at and identify what's going on here is helpful. Okay, now I've lost my screen, but I guess I can use the screen behind me. So I think it's important to still make the color image, even though we can access the catalogs. We still want to be able to make the color image. So I'm going to run through the process of processing your raw data set rather quickly. All of the tools that we have in here, and then we'll go to color combinations of images. So all of the things that we can do that are useful in this lab for processing star cluster images. To start with, just being able to open up FITS images and inspect them. So we can see things like in this case, there's a bad column. There are actually a few bad columns on that CCD, but you can see that in here. So it's a web-based software that your students can access easily from anywhere. They have the internet, so they don't have to install anything, and they can check out their FITS images in Afterglow. There's this new cosmetic correction tool that Vladimir and Dan and Dan's other second year physics undergrad built the code for to run cosmetic corrections and clean up bad pixels, hot pixels, bad columns, stuff like that. And so it's basically just click on that and hit the submit button to clean it up. So there's a cleaned up version of that image, which has removed the bad column without having to click anywhere or define anything. It hunts and finds all of the bad stuff all on its own. And then it'll run WCS calibration. These images were a couple years old, and we had a moment there with Skynet where there was a bug and it was causing WCS that came out of the pipeline on Skynet to be sort of diagonally offset. It was a zeros and ones column thing. Anyway, and depending on which they're on German equatorial mounts, and so depending on which side of the sky the image was taken, we had this sort of offset. Anyway, so when I was processing these old images, I had to run WCS calibration, but there's a WCS calibration tool, and you just select all of the images, running a plate solve mode, extract the center from the current image, and then just click submit and run WCS on all the images. And then once we have a better plate solution for all of our images, we can run WCS based alignment. And so there's an alignment tool in Afterglow. And in this case, my images were all taken from the same telescope, but they were all taken at least an hour apart. So there's a little bit of offset in the pointing for all of the images. And so we want to crop the outside, and I guess I enabled skew and whatever those other options are. I can't read them on the screen right now. But yeah, run alignment. And so I aligned all the images, and that's just a click away. In addition to WCS based alignment, depending on the types of images that you might be analyzing, like the moon, May ran a workshop yesterday where she aligned images of the moon and made a mosaic, and that used features based alignment, but there's features based, pixel based alignment, and auto source extraction. So the alignment tool is very useful. And then stacking, so we can select all of our B filtered images and stack them together and create a stacked image in B and V and R and I. So I did all of that. And then we can group our stacked images together. So just by selecting the B, V, and R, group them together in order to make a color image, and colorize each layer. And that's just right click, color map, and then called the B1 blue, and then right click color map, call the R1 or the V1 green, and the R filter image, stacked image red. And then once we've colorized images, clicking on that top layer there, I guess I can point with the mouse so Terry can see. Clicking on the top layer there shows a color image with whatever the default color blend is. Now, You can actually see over here, though, that the image histograms are different for the red, the blue, and the green. So what this histogram is showing is the number of pixels in a bin with whatever pixel value, and the peak is where the background is on the image. So that you get your background is a whole bunch of low pixel count red and low pixel count blue and green, but there's more background in the green stack. And so in order to properly combine them, we actually want to align the histogram to get the equalized backgrounds. And there's also an even cooler thing that we can do. So to start with, we just link all of the layers together by their pixel value. And then in addition to running a background neutralization, we've actually got built in here, because Afterglow will also do field calibration for all of your images. So it'll access APAS, for instance, for your BVR images, access APAS and measure the 0 point for each image. And if we measure the 0 points for each one of the images, so that we've got a magnitude in B and a magnitude in V and a magnitude in R for each one of the stars, then we can do a color combination that's based on their measured magnitudes and produce a realistic color for each one of the stars that's based on a black body that peaks in the B and ends up looking white with the Planck tail of the Planck distribution. So so we calibrate our colors based on the 0 point measurements and create a realistic color that's not based on setting your average star to be white, which is what astrophotographers will often do, sort of adjust colors so that stars on average look white, but we're actually using our science filters to make quantitative measurements, and we have quantitative colors that we're displaying, which is neat. So once we've done that, you can see that the histograms actually line up. So they align with each other, and then we can adjust like our contrast settings and whatnot, and make things look a little bit nicer. There's also another thing here that's really cool. With Cluster Pro Plus, when you fit an isochrone model to your star cluster, you can actually you determine the reddening value. So in addition to producing true colors for the stars as we see them from Earth, we can also pull back the veil of the interstellar medium and look at the stars the way they would look if there wasn't a whole bunch of dust in between us and the cluster. So you know, which helps for interpreting colors. So I've set it to 0 there and produce this image. We can adjust contrast settings to produce an image that looks like that. You can see there's a planetary nebula in there. And so that right there is the image that I produced in whatever, something like 25 clicks. Makes a really nice image. I don't know if this will change. Oh yeah, that does. You can actually see that difference. So this is the reddening for this cluster is like 0.12. And so you can see that that the blue stars are whiter. And when I go to the next one, it's faint because the reddening is only 0.12. But the bluer stars do get bluer. You get a more realistic color for the white dwarf there at the center of the nebula. Anyway, so those are the basic steps. So Afterglow accesses image processing tools. The basic highlights are that we can take images from Skynet. They're automatically reduced. So you submit your observation to Skynet, and Skynet's pipeline will automatically do the bias, flat, and dark reduction and WCS calibration, and now it's more accurate than it was a year ago. And then there are all of these essentially like one-click image processing features that are built in all of these tools. So the cosmetic correction, WCS recalibration, if you want a more accurate WCS, aligning and cropping images. When we stack, you can do, there are smart stacking features so that when you add images in, because we want to use them for photometry, rather than flipping through the images and determining which ones look better and which ones look worse, it'll actually, the smart stacker will look at the different images and determine, does this one improve my signal to noise or does it make it worse? And then it just rejects all the ones that make the signal to noise worse. And then there's also statistical rejection tools for cutting off the tails and all of that. So when we produce a stack, grouping images and colorizing and running the photometric color correction with or without de-reddening. And then some very simple, easy to use, nonlinear contrast adjustment tools for making a pretty color image that's a lot easier to use than GIMP, for instance, or whatever other tools that people use. Okay, so we're gonna try it. I'm not gonna have you take the images, the raw images, and run through all of those things. I've got instructions here for just accessing some previously stacked images and making a color image. And since I showed you for M46 already on the screen, I figured it'd be more fun to do a different one. So at the top left of Afterglow, if you click the Open Files button, then navigate to Files, Sample, MWU, Module 2, IC2948, and then just open all the files. Or you could actually just open BR and V if you want, because we're not going to use the I-band image that's in there. We could. I can just demo this too, because I have my slide with the instruction steps. There. Do you all want the instructions up or do you want me to demo? Maybe leave the instructions up? Yeah. Oh, shoot. Yeah. All the Cluster Pro Plus stuff. Yeah. Okay. Okay. Yeah, I guess you didn't need a Skynet account until right now, technically. Just BVR. You could open all four, but then you're going to group the BV and R together. How are you doing, Terry? Oh, if you just click on the top layer, yeah, then it'll bring it up. If you click on any of the images, it'll display that. Yeah. Yeah. Yeah, just work through the whole thing. You got it. Oh. Rather than that, I think, yeah, log in via Skynet. Yeah, grant app. Right. Yeah. Color composite tools is up top right. Oh, you need to hit the display. Yeah, show display. Am I missing that? I think I am. Oh no, click display tool at the top right. Yeah, it's 2 steps in one, that's why. Which one? Finger. No, don't bother grouping the eye. Yes, yes. And then the 3 dots, that. Yes, and then group selected file. Yes.
Oh, I did.
There, now they're grouped. Now, if you click on the top level one, there's and then click this and zoom to fit button. Yeah, that one. And that loads it. Yeah. Yes. Yes, yes.
And understand.
Okay. You're doing that. That's the color composite tools business.
Okay, so here we go.
Oh, that's the one that you're on. Yeah, the display settings. These are all the tools. Essentially, yeah, so you're on it. Mm-hmm. Yep. Oh yeah, click. Yeah, you already had it.
Color composite tools. Color composite.
So click here. You have to be on the top layer. And I would click the zoom to fit button. Now here's the color composite tools. So here's where you're gonna adjust the histograms.
I gotta tell you that this is so freaking cool. I'm gonna t-shirt.
Awesome.
I've been trying to design this.
Yeah.
For over a decade.
Mhm.
I'm a student.
Yeah.
And that plus that's the future.
Awesome.
Color.
Awesome. Oh, that's wonderful. Thank you very much. What's that, Matt? We don't yet. No, we're gonna do that next.
Okay, so next we have to do.
Yeah, with yeah, link all layers pixel value because there's a percentile one.
Photometric measures of Field calibration?
Yeah. Just takes a minute, and you might have to scroll down to see. Yeah, so it's running. and- Okay, then you can just click calibrate color.
This is so much better than the Afterglow of a few years ago.
Yes, yes. It's afterglows come a long way.
Wow, I bet.
Uh-huh.
We don't have the old movie that does it.
It doesn't. Oh,
I don't know what calibrate color
Yeah.
is.
okay, so you've got the color calibration done, I
Yeah,
think, already.
I did the 0 point correction.
So yeah, scroll down. There. Oh, actually, and to make this bigger, another cool thing to do, hit Command minus about 3 times. There. And it makes this smaller, but you can adjust your zoom on the
Make
screen to
this-
create more space for this.
How do you make this bigger without making that bigger?
So you just click it's maybe a bit too small, right? Oh, no, it's just, you just have to move the window up and hit the zoom to, but click the zoom to fit button down.
Oh,
Yeah.
yeah. Okay. So now
Okay.
I'm looking for.
So now you,
Stretch mode, calibrate colors.
yeah,
There's a-
so that's just your screen stretch.
Is there a calibrate colors command though?
Um,
I don't
that was,
see anything
that was the
says
one that
that.
that was in the color composite tools.
Okay, well, I must
Yeah.
have already put
Yeah,
that,
you did.
and so
yeah.
then we're gonna go from.
From
Stretch
linear
mode to-
stretch to a mid-tone stretch,
Alright.
which
The log,
you could play with the log or the art sign or whatever, but mid-tone works the best.
you know,
And then if you click the default settings, there, and then I figured background 20, mid-tone level 90 does a really nice job. But now this is all just art.
So that explains settings,
Mhm.
which is that.
Yeah.
Where's the color composite tool?
Oh, you have to be on the top layer.
Oh.
The combined,
Oh,
the actual combined one.
Oh, okay.
Yeah,
That
I
makes
might have
sense,
missed
yeah.
that. Oh,
But I
no.
don't know why my lower right corner is just taking a long time to load. It just isn't there.
Hmm.
Anyway,
Yeah,
guess I
sometimes
can
it
continue.
hangs.
okay, so now oh.
Now
that's
it's there.
enough. Okay.
Yeah.
So where is the stretch mode? We can't hear online?
Terry, can you hear me now? No.
Yes.
Oh, you can. Okay. Yeah, the battery's dead on this thing. So do we have any? Okay.
Hello? Can you hear on Zoom? Hello?
Yes. Yes.
Okay, thanks, Terry. Thanks for saying something. Yeah, I did. Okay, so just for the last few minutes, so the way that you can actually find the distance is to look for the distance at which, when you have already isolated in proper motion space and you've got the range cutoff selection happening, just move through distance values and see what the distance is at which you have the most stars. Now, I'm not sure why this is, I guess it's not very fine. What's going on here? Something is frozen. Oh yeah, there. It was frozen. So you can coarsely move through here and just look. The distance to the cluster is the distance at which there are the majority of stars. Something is lagging though. But so you can coarsely move that and then sort of fine tune and go up and find the distance where we get the most stars. Yeah, there it's going down again. So I had a 335. So call that roughly our distance. It's the distance at which the majority of stars that are moving with the cluster exist. So it's the best that Gaia can give us for the distance to this cluster. And then we just want to fit our isochrone model. This is obviously young. You saw that it's a star forming region. It probably has high metallicity. The isochrone model isn't updating properly. Oh, and I'm only got a minute left. Oof, it's really lagging. I'm not doing anything there. Okay, there. So then just change the reddening. What I found is somewhere between 0.3 and 0.4 seem to fit pretty well. It's a young cluster, so it's hard to fit the isochrone model very accurately because there are the variation in age is quite large compared to the age of the cluster. So you know, it's just harder to fit star forming regions. But there we have something pretty good. This is the value that we were wanting for Cluster Pro Plus. So over here, you could go back to the display tab to color composite tools. And I first of all have to link my layers. But then if you go to photometric calibration, you can enter in that 0.4 right here and update your colorization with extinction removed. I'll calibrate colors. I currently don't have my colors turned on. Blue, red, and green. And then if I zoom to fit, go to mid-tone, hit the default button. I think I said I like it when it's at 10 and 90. That's 9 there, something like that. It's maybe a little bit too much, maybe 95. anyway, and so that's what I get with reddening removed. That was the second last thing that I wanted to show, and I'll just show you one thing quickly because we're actually a minute over time. So I'll just show you for 1 minute the very last slide. So the second last slide said to set reddening to 0.4, and then the very last slide says that you can do this for yourself. So I've written, if you go to this link here, there's a full manual that essentially runs through background, everything you need to know about isochrone models and star clusters, and how to identify like the unresolved binaries and all of the sort of background theory. And then there's and some examples to work through and practice fitting. And then once you've done that, there's a section on setting up observations in Skynet. This table 1 here shows the ideal right ascension range for observing at different times of the year. So right now is somewhere around between 11 and 19 hours right ascension. And then we do have a curated list of clusters. Some of the images aren't great, but most of them are pretty good. And where we've got about 130 open clusters that we've imaged and created a catalog of, with estimates of sort of an optimized exposure time for the prompt telescopes on Skynet. And so go through, find a cluster if you want. Find a cluster. There's a table of open clusters, and there's also a table of globular clusters. Find one in the right ascension range. Choose it. We've got the exposure times there. You can scroll through. Most of them are imaged in BV, RI, G prime, R prime, I prime, Z prime. Scroll this way to see all of them. These are the exposure times that I'd recommend for each of these clusters. Pick one that you want to take some pictures of, and then go into Skynet and add an observation. The steps to do that are described in detail in this manual, what to do, and then the short version is the very last slide. So you've got the link to the clusters. You can do the scrolling. You can choose your cluster from there, and then log into Skynet and submit your observation. And this is just set up to image once in each filter, leave an hour between, and then do it again and again and again, and repeat 5 times. The reason we do that is sort of for like dithering purposes, and also in case there's not optimal sky conditions. So if you get 5 images that are taken with at least an hour between them, then you've got a better chance of having really nice images in at least 3 of them to make a median. And when you do the stacking anyway, and then you can take them and make color image and do the photometry. Anyway, you all have Skynet credits in the accounts that were created, and so an instruction manual to mess around with. And that's all. Thank you. Sorry, everything went really quickly at the end. Hopefully everybody got what you need. And if you have any questions, I did have an email address on one of those slides. Send me an email. Terry, I owe you a response on an email you sent me yesterday. And I'll get back to you. But yeah, if you have any questions about this, let's happy to hear from any of you. Oh, yeah. We actually have 2 plugs. So Dan was just saying, for those of you online, tomorrow doing some serious astrophotography on star forming regions. So come to the workshop that Dan and Matt Fleener are gonna be delivering tomorrow morning. And there you'll get to do some more advanced astrophotography of star forming regions, which is a lot of fun. And then the other thing is, one of the projects that we're going to be working on here over the summer and the next little while is the star cluster catalogs that exist aren't great. Our parameters, what we know about them. So we want to set up a journal of some sort for student projects. We're not exactly sure what it's going to look like. What we're going to do over this next few months is meet every week as a group to discuss how to make a catalog that students can do projects using this tool and actually update our parameters and things that we know. So if anyone's interested in joining our group to talk about and design that, send me an email, let me know, and you can be a part of the group for that. Okay, all right. Have a great day, everyone. I think this was the last session, wasn't it? And then we've got trivia in 22 minutes and then the walking tour for those of us who are here. Coffee and posters over at the room for those of you who are online. I'm not sure if there's anything more that you can access in all of that. Certainly not the walking tour. Oh, trivia can be done online. So that's in 22 minutes. Anyway, thanks for coming. Have a great day.
Great. Thanks a lot, Daryl.
Yeah, talk to you soon, Terry.
You bet.
Yeah. There. Stop share. And then is it recording? Yes. Stop the recording.